Okay, and this, I think, is the final interpretation as a generalized convex clustering method. So in convex clustering, you are given a data set, and this data set consists of feature vectors, which I denote here by A. A superscript 1 is the first feature vector, A superscript 2 is the second feature vector, and so on and so forth. And then you try to cluster them by introducing a copy or let's say a guard for each of these feature vectors, and this guard is a local model parameter. And then what you do is you minimize the pairwise distances between these guards, between these local model parameters, while at the same time penalizing if you pull away the guards from the corresponding feature vectors. So this W1 at one point should on the one hand be close to A1, but on the other hand should also be not too far away from the other weight vectors. And to balance this, you minimize this combination of those two terms. So the second term here, this total variation term, measures the discrepancy or the non-clusteredness of the model parameters. And the first term measures the pulling away of these model parameters from the original data points. So this model parameters should be close to the original feature vectors, but at the same time should be clustered. And that's called convex clustering. And GTV minimization generalizes this by using a more general loss function. So convex clustering uses this loss function, and in generalized GTV minimization, we use here a more generic loss function. Yeah, also note that convex clustering, as introduced originally in this one of these papers that I refer to here, this uses the Euclidean norm. This is different from the squared Euclidean norm that we will mostly use in this course. And using the Euclidean norm turns out to amplify the clustering tendency. So when you use here the Euclidean norm instead of the squared Euclidean norm, the result will be more clustered. One drawback is, of course, then you cannot solve this problem here with gradient descent because there is no gradient of the norm at some points. So you can only use subgradient descent, which are typically slower.